Hey everyone! Today I want to talk with you about the boost converter circuit, which is a cousin of the buck converter. I did a video on the buck converter a few days ago, and conceptually they're quite similar circuits. Now, why is the boost converter circuit so useful? Well, let's say I have 3-volt battery cells and I wanted to generate 12 volts. How would I do that? Well, an obvious way to get that 12 volts is I could take 4 of 3-volt batteries and stack them up together in series to create 12 volts. But that would require 4 batteries and it would take up quite a bit of space. And so you can imagine that if I had a boost converter circuit, I could simply take one 3-volt battery and up-convert it to 12 volts. And yes, it might require additional components like an inductor or capacitor, 2 switches, but it wouldn't take up as much space as having 4 battery cells. In automobiles, let's say your Toyota Prius or Tesla, you have motors that require 300, 400, 500 volts. And so it'd be unrealistic to take a bunch of battery cells and just stack them in series in order to generate that much voltage. It would just take up way too much space. And so that's why boost converters are very useful. It's a very useful invention. And so today I wanted to go over conceptually how the boost converter works and maybe do some circuit analysis to calculate what the voltage output is with respect to the voltage input. So let's get started. To start off, what does a boost converter or step-up converter look like? Let's draw it out. So here we have a simple realization of the boost converter circuit. We have our voltage input, inductor, a switch, which can usually be implemented using a transistor, diode, capacitor, and our load. And here's our V input, and it should generate a larger V output. Now, how does this switch work? Well, if you watched the buck converter video, you'll know that this circuit will switch on and off with a certain duty cycle. And that duty cycle will help to determine what our output voltage is with respect to our input voltage. Now, it is useful for us to plot what the signal of the switch behavior looks like. On, off, on, off, on, off. And I'll draw it here. Now, this signal is to represent the behavior of the switch. And when the signal is 1, that indicates when the switch is closed or on. And when the signal is low at 0, that indicates when the switch is open or off. To have some notation, the period during which the switch is closed or on, we will call that time interval T on. And the time interval when the switch is open or off, we will call that time interval T off. So let's draw that here. So T on and T off actually add up to the total period of the full cycle of this switch behavior. And that period will actually determine certain properties about the boost converter circuit, such as its efficiency, the size of the components we would need, for instance the inductor, but we're not going to go over that in too much detail in this video, but just so you know. Now, just to give you some intuition on how this circuit works before we get into the math, what happens during the T on period when the switch is closed for this circuit? Okay. So let's say we're in a T on state and the switch is closed. What happens here? Well, it's quite simple now. Basically, this point is short to ground. Let's call this ground. And you can ignore the rest of the circuit. And all you have is a closed loop with the input voltage source as well as the inductor. And the inductor, being an inductor, will try and fight the change in current. And so because the source is now only connected to the inductor, it's going to try and drive current through this inductor. And at the same time, a voltage will be applied across the inductor to fight that increase in current. And so the polarity across the inductor would look like this. Make sense? what happens now when the switch is opened or turned off? When the switch is turned off or open, what will now happen is now the source and the inductor see a larger impedance over here, which means that the current running through the inductor will tend to decrease because the impedance it's seeing is now increased. However, the inductor, being an inductor, will try and fight that decrease in current and apply its own voltage. And so because the inductor is now fighting that decrease in current that is about to happen, a voltage will be applied with this particular polarity, opposite to what was happening before. And if we take a look at this, we see immediately that the voltage output will actually be the sum of Vin and VL, the voltage across the inductor, which intuitively tells us that Vout will be larger than our V input. Hence, boost converter. So hopefully this explanation can give you a little intuition on how this circuit works. But now, let's do a little bit of circuit analysis and math in order to prove our intuition is correct. So now we're going to go into using Kirchhoff's voltage laws, KVL, in order to solve what Vout is with relation to V input. So using KVL, we're going to write out a system of equations in order to determine what our V output is with respect to our input voltage, as well as the duty cycle. Okay, so let's take a quick look at the circuit. So in order to perform KVL on this circuit, we're going to assign voltage polarity across each of the components in our circuit loop. And so for our VL, we're going to assign positive polarity to the left side and negative to the right side of the component, like so. Do not confuse me assigning polarity across the inductor with what I was explaining earlier. Early on, when I was writing polarities, I was explaining to you how the voltage across the inductor reacts in response to the change in current running through the inductor. And that's a separate concept. Now we are setting polarities across this inductor to perform KVL. And as long as I'm consistent with my polarity across the inductor, in all of my equations, my Vout will be correct. If I wanted to, I can also assign positive to be the right side of the inductor and negative to be on the left side of the inductor and solve all of my equations with that polarity. As long as I'm consistent, my Vout answer will also be the same. If you don't believe me, you can do that calculation yourself. But in this video, I'm going to be consistent and make sure that the positive side of the inductor is the left, negative polarity will be assigned to the right of the inductor. Now I spent some time explaining that. If you still don't understand, don't worry too much about it. It will probably come to you, but just keep in mind for KVL can be a little tricky. Okay, so let's start off with the T-on case and do KVL on that circuit. So during T-on, my switch will close. And if we performed KVL on this loop that we have here, it's closed, so we ignore the rest of the circuit on the right, our KVL equation gives us the following. V in minus VL equals 0. Now, what is VL? By definition, VL will equal to the inductance L multiplied by the rate of change of the current with respect to time. And now we're going to do a trick similar to what we did when we were talking about the buck converter in a previous video. Because t on and t off time intervals are so short, we can actually set dt to be equal to the time interval t on. And we can substitute di for the delta current, delta I 1, let's say. Now that we have this, we can take this VL and substitute it into this equation. Now we have our first equation. Now that we've performed circuit analysis for the T on case, what happens during T off when the switch is open? When the switch is open, what does our KVL equation give us? Well, now we have V out here. Because this circuit is closed, this diode would turn on, and we can easily perform KVL using the voltage drops Vin, VL, and V out. So this is the simple KVL equation that we wrote with the switch being open. Vin minus VL minus V out equals to 0 to complete the loop. And now, looking at VL, we can set this equal to the inductance multiplied by the change in current with respect to time, similar to what we did during the T on case. And similar to what we did during the T on case, we can actually substitute dt for T off, which is also very short time interval. And we can substitute di with delta I2, the change in current that through the inductor that happens during T off. And then we do the same thing where we substitute VL into this equation here. So now that we have two equations, what's next? Well, again, if we refer back to when we were looking at the buck converter, there are some variables that we would like to get rid of in these two equations. And what are they? It would be delta I1 and delta I2, because these are the only variables that don't seem useful in our final answer. So what is the relationship between delta I1 and delta I2? Eventually, this circuit, when it's switching on and off, eventually this circuit will reach a certain steady state or equilibrium, where the amount of energy that's stored in the capacitor and the inductor will be constant after each on-off cycle. That is equilibrium. If the components, like the energy stored in the inductor, is constant after each on-off cycle, then that also means the current going through this inductor will also remain constant between each on-off cycle. And so if I plotted the current as a function of time, we will see that the net change in current after each on-off cycle is 0. So I'm going to plot the current through the inductor on the right to give you visually what's going on. Let's say I have IL going through this inductor here. Now I'm going to plot current IL, and you can see that during T on, the current through the inductor will increase. Okay? And during T off, the current going through this inductor will decrease. And so on and so forth. And if I line them up, you can see that the net change in current IL after each on-off cycle will be 0. And so that means that delta I1 plus delta I2 will equal 0. And there you have it. We have 3 equations. We're trying to get rid of these 2 unknowns. And so that should be enough for us to solve for the final solution. So let's do it. I'm going to take equation 1 and get delta I1 on one side and all the other variables on the other. I'll do the same with delta I2 with equation 2. And then I'll take delta I1 and delta I2 and substitute them into this equation here. So from these two, I have delta I1 and delta I2, and we will substitute both of these equations into this third equation here. I think I'm running out of space. Notice that the inductances can cancel out. And I'm gonna make it weird. I'm gonna write the final answer up here. Okay, so after a bit of number crunching, we have the final answer. V out is equal to V in times T on plus T off divided by T off. And let me clear the board a little bit to explain this equation. So we have the solution rewritten here, but if you look at it carefully, you'll realize that if I want to write this as a function of duty cycle, then the answer would be equal to the following. V out equals to V input times 1 over 1 minus D, where D is the duty cycle, T on over T on plus T off. And so there you have the answer. Yay! I hope that was interesting. It's always very fun to think about boost converter circuits and buck converter circuits because of the way the role that the inductance plays. It's a pretty ingenious circuit, and it's amazing that you can kind of take a smaller voltage and just increase it to a larger voltage. And you're not breaking any rules here, you're not breaking conservation of energy. By having a larger voltage, you're going to also have a smaller output current. So it's not like you're making something out of nothing. But it is pretty cool that this works. I hope you had a great time learning about this circuit with me, and have a nice day.